Good afternoon, everyone. I'm going to be discussing my capstone presentation today, which is investigating the global determinants of tuberculosis and tuberculosis HIV co-infection using machine learning models. My wonderful advisor, Dr. Pinky, was very instrumental in this capstone project today. So let me give you some quick highlights. My analysis window for this project was from 2015 to 2023 with its data. I had 4 continuous outcomes, and this is a regression model. And I had 1,385 observations between multiple data sets, and 173 countries are being represented. Okay, so tuberculosis or Mycobacterium tuberculosis, is a very infectious killer, and it is one of the leading ones in the world, especially when HIV comes into play, because it causes severe immunosuppression, which can accelerate progression from latent to active disease. And so globally, there are around 10.8 million cases just in 2023 alone. There are about 1.25 million deaths in 2023 from tuberculosis. And people who are living with HIV, which is PL-HIV, their risk is around 16 times higher just from having immunosuppression. So the burden is highly unequal around the world. And so some things that I'm going to be talking about are how low resource settings can carry the greatest exposure, delayed diagnosis and treatment gaps in different countries, and that can really amplify people's mortality and diagnostic complexity. And so why this project matters, it's linking epidemiology, country development, and socioeconomic factors, and linking them into one kind of diagnostic frame. And so that's what we're going to talk about. So some research questions that me and Dr. Pinky have been working on is where, how, and who are more likely to develop tuberculosis and tuberculosis with people living with HIV, and why. And then also what socioeconomic factors are most influential in tuberculosis incidence and the mortality. So here is just a basic framework of kind of how we move through this project. So we looked at structural conditions in the data set, looking at HIV epidemics, where they're more concentrated, and also looking at the general outcomes. And then kind of the data part of that is, data integration, then creating your machine learning models and kind of using those as actionable priorities and insights for, healthcare providers and us as scientists. And so our working hypothesis was that tuberculosis incidence and mortality should significantly rise where life expectancy tends to be low, child mortality is high, and access to care or infrastructure is weak, because these are very good socioeconomic indicators for different countries. And also TB HIV incidence and mortality should primarily be driven by HIV incidence, prevalence, and its related health system coverage variables. And so some just general literature gaps. The data set obviously is a temporal type of data set. And so as the years go by, there would be less kind of inputs of data for more current years versus previous. And also every country has different infrastructure as far as, having data collection essentially, because there's different GDPs that go into their health infrastructure. And just a lot of the studies for TB HIV, they only kind of really relied on one country. And so it was really hard to find a lot of literature that was around this topic as well. So we're hoping to become a more novel thing in this. And so going into data assembly and the overall methodology, I kind of took 4 different data sets. So we had WHO, which is the World Health Organization, TB burden countries data set, and the World Health Organization rifampicin TB burden estimates. And then also we had 2 World Bank indicator tables, which were merged on country code, and the year. And so throughout merging these 4 different data sets, we had a final EDA panel of 1,385 observations, 104 columns, and the 173 countries. And so kind of the exclusion logic into going into the actual modeling was dropping unnecessary variables that we thought could cause co-founding, and also ending in low and high to avoid using interval estimates as predictors. We also did not use country or country code, and I retained WHO region just to reduce the amount of missingness in the data, since they were from two different overall data sets. So the outcomes that I'm predicting are E incidence, which is estimated TB incidence rates, E mort, which is the mortality rate of tuberculosis, and E incidence with TB HIV, and E mortality TB HIV, which is with mortality of TB HIV. And the imputation and scaling, EDA preserved the raw missingness of the data for inspection purposes, but when I went into the modeling, I obviously removed a lot of features and a lot of things like that. So I also did forward fill and backfill imputation, and categorical predictors were one-hot encoded. Linear models use standardization as well, and tree-based models were used without any type of scaling. Okay. So my training set, as far as like the kind of temporal split of the data, I had a training set of from 2015 to 2020, which was the bulk of my data, obviously. And so I had around 1,033 different rows for that. The validation was around 167, and a test set was 185. And so why was time split important here is because it's based on time series data. And so obviously as the years go on, there would be less data to work off of in more current years versus from 2015. And so some of the models that I used were linear regression, random forest, extra trees, gradient boosting, XGBoost, history and gradient boosting, and elastic net. And then the evaluation metrics being that it is a regression type of problem was root mean square error, MAE, and R squared. And go to the next one. So EDA findings, as far as just general findings, there was obviously a lot of skew in the data due to missingness for some countries such as Afghanistan, and a lot of Middle Eastern countries. But overall, the country and region with the highest incidence was Northern Africa and Sub-Saharan Africa, with tuberculosis cases that were drastically higher than most other countries. It is important to note that the USA was not included in this data set because the World Health Organization did not have a partnership to get that data for this specific data set. Okay, so I also built kind of GIS modeling just to kind of present as well. So I went through and kind of looked at the incidence, mortality, and for each country and kind of built a GIS kind of interpretable model that I can actually kind of demonstrate. So if I can quickly show you guys. So I kind of built it to where you can go through each country and look at, kind of the incidence of each country for the year 2022. Obviously, I'm trying to build this as well for the other years as well. But I thought it would be just an easy way for people who are using this in the future to kind of build off of their data set to get a visualization of what's actually happening versus going through the entire data frame. Okay, so let me get back to our presentation. Okay, so temporal patterns in the geographic story. Obviously, as I explained earlier, incidence showed a steep decline in 2023 due to the lack of overall data in the data set. And it was much more sparse compared to the other years. And generally, you had a very consistent decline up until around 2020, where there was a little bit of an uptick in mortality, but then it ultimately started to go back down. So that's kind of something that I'm going to look into more for my PhD work as I continue this on with Dr. Pinky. And so as far as the results and discussion, we actually had a very good turnout as far as the test R squared value. I went through all of the models for each of the different sorry, predictors, and extra trees won 3 of the 4 tasks, with TB HIV incidence having a R squared value of 0.909, TB mortality was at 0.847, and TB HIV mortality was 0.840. Random forest was the best for TB incidence specifically, as it had an R-squared value of 0.827. And so this kind of shows that ultimately non-linear ensemble models clearly outperformed a regular linear baseline model, which means that there are very complex interactions driving the different tuberculosis incidents across the world. So kind of going into the predictors, there were a lot of different predictors. I had a data set of around 107 columns. But after removing co-founders and a lot of the different duplicates and low and high bounds and things like that, I ended up with a total of 57, which is still pretty good for the data set. And just kind of looking at the predictors, the top ones ultimately across really all of the boards were life expectancy at birth, which had a very influential and impactful the kind of prediction importance, permutation importance, followed by access to electricity. And then you have global domestic government expenditure, health expenditure specifically, things like forest area, adults that were newly infected with HIV, just all types of things. And so those are the kind of predictors that we were looking at to see what is the most influential in tuberculosis infection across the world. And these are kind of the ones that were seen as the most important in the modeling aspect. So to kind of wrap this up, some conclusions that I found doing this capstone were that sub-Saharan Africa has a very high transmission rate among other countries, and there's a strong HIV transmission rate as well. And this is some of the drivers ultimately come down to having lower socioeconomic status and health infrastructure compared to other Eastern European countries, or even parts of like Russia and things like that. TB burden is obviously exacerbated by low health investment as well. The less money your country spends in kind of solving these issues, the more incidents you will have and burden. So future direction that I'm kind of using to take this into my PhD with is to kind of look into more of those subnational data sets to reveal the actual within country heterogeneity, and to kind of bring in more treatment coverage and health workforce variables that are tied to actual healthcare delivery and service, to kind of see what is actually going on within these countries that have deemed lower socioeconomic status, to see what exactly is responsible for those things. And so the bottom line is that reducing TB will require a lot of structural improvement and stronger healthcare systems. And while reducing TB, HIV specifically requires HIV prevention tactics, antiretroviral therapy coverage, and TB screening treatment in the same places and population sets. And so those are just kind of the things that I've been working on for this capstone. And so it's just an acknowledgement. I do want to thank Dr. Pinky again for being so helpful in this, and the World Health Organization and World Bank for having openly accessible data. A lot of them were not openly accessible, which was really interesting to see. But also just my professors at Meharry for teaching me the kind of core curriculum to even develop this capstone. And so I thank you guys all for that. I know that was a lot of information for 15 minutes, but I do want to say, does anyone have any questions for me as far as the work that I delivered today?
Thanks, Collin.
Thank you.
Excuse me, Collin, I didn't have a question. I just wanted to say the work was excellent, and I liked how you had the presentation. It was really clean on the
Thank you very
slides.
much.
Mm-hmm.
Yeah, that was the hard part. I was like, how do I present such complex interactions? It's like, I don't know how to make this clean, but hopefully it came across as clean as possible.
You did a great job on the organization. It was definitely organized very well.
Thank you, Brian.
Colin, what are you expecting to do more with the GIS mapping?
Yeah, I kind of did that just for the capstone to see like how can I actually, kind of get more into visualizations. I know we worked a lot with that with Dr. Levin, and so I was kind of include some of what I've learned from his course and to see how can I present this to where it's actually, we're all data scientists, but like if someone was watching this that wasn't familiar with this, how would they know where the incidence actually occurs? And so I just kind of want to build off of that to kind of see um, like more complex interactions, I guess, country to country, or is kind of looking like, okay, these countries border, what are their interactions and what's causing, certain things to create higher TB burden ultimately. And so just kind of developing a more complex map, I think, that people can just access to see what is happening and why is TB so rampant in these countries. So that's ultimately my goal.
Thank you. Good job.
Thank you. Any more questions?
Okay, looks like that's not the case, but thanks,
Oh,
Colin, for the
I
presentation.
appreciate it.